Welcome to Organic Chemistry. In this video, we dive into the concept of chirality. Let's begin. Of course, isomers share the same chemical formula, but they differ in the ways that those atoms relate to each other. Some, of course, differ by their setting or placement connection. These are the constitutional isomers, which we began the year with. Others by orientation in space. These are called stereoisomers. Within stereoisomers, we have two distinctions. Configurational stereoisomers, which are different substances entirely, or conformational stereoisomers, which we have seen as occupying different conformers of a given substance, different states of being. Within the configurational stereoisomers, we have diastereomers, which are not mirror images, and enantiomers, which are mirror images, being placed in opposition to each other. Our own hands mirror each other. They are identical in their parts, yet they are impossible to superimpose. This impossibility is the definition of chirality. Left and right hands are equivalent in composition, but opposed in orientation in space. And we call such pairs enantiomers. If a molecule can be reflected and yet remain identical to itself, it is achiral, not chiral. Possessing a mirror plane, then, means possessing this self-symmetry. Not every absence of symmetry is chirality, but every presence of symmetry will always cancel it. So we turn our attention to the sp hybridized atom. It defines the line. Locally, it is always symmetrical, and thus always achiral. Yet, even to the right, if we pay attention, global asymmetry can emerge when the linear arrangement is changed at the ends. Allenes, for this example, are not ordinary. Each carbon is indeed linear, locally symmetrical. Yet the entire system twists into a form with handedness. The perpendicular p orbitals forbid equivalence by rotation, and the molecule as a whole is axially chiral. In sp2 geometries, local symmetry is again evident. Trigonal planar geometries meet their mirror images perfectly, simply by rotation. There is no chirality here. Every reflection is matched by itself. So far, we've used examples as if the shape of the molecules were fixed. But real molecules are not sculptures, they are in constant movement. Sigma bonds, of course, can usually rotate, sweeping through many conformations. Look at this molecule in the mirror. In this frozen pose, it looks chiral. But ask yourself, could I rotate around that central bond and line it up with its mirror image? But the real answer is It depends. If that sigma bond can spin freely, any chiral pose is just temporary, a blur that averages out. But when bulky substituents crowd the bond, rotation can be hindered or effectively blocked. Now the two mirror image conformations are trapped. They cannot interconvert. They become distinct enantiomers, separated not by composition, but by the restricted rotation. And this is another form of axial global asymmetry. Chirality born from a whole axis being locked into one form of handedness. In addition to axial chirality, we also have planar chirality and helical chirality, all forms of global asymmetry. A ring system with restricted motion can be planarly chiral if its mirror image is different, even though each ring system on its own may be achiral. But perhaps the most important example for us is that life itself is built upon chirality. The DNA double helix is right-handed. Proteins fold into right-handed alpha helices and with specific arrangements of beta sheets. Change the handedness and you change the way these molecules recognize partners, bind onto substrates, and catalyze chemical reactions. It is totally not a side note in biology, but written everywhere about our very form. But now we arrive at local asymmetry, what is defined by the sp3 hybridized atom having 4 unique substituents. If they only have 1, 2, or 3, these will never be chiral enantiomers. But once we have 4 unique substituents, they will always yield a pair of enantiomers. In order to identify and name these enantiomers, we refer to the same Cahn-Ingold Prelog rules that we had introduced at the beginning of our discussion of alkenes. Now that we see chirality, we must learn to name it. Every chiral center can be described as turning right, Latin rectus, or left, Latin sinister. We arrange the lowest priority group, often hydrogen, behind. Then trace from highest to lowest atomic number. Clockwise would mean to the right, counterclockwise to the left, S. According to Cahn-Ingold Prelog rules, we compare atoms directly attached. The one with the higher atomic number wins. If tied, we move outward until a difference appears. Always look with the lowest priority group pointing away. But be careful. Not every apparent asymmetry is true chirality. Some molecules shift conformations freely, mirror images of a single moving form. Others contain chiral centers, but cancel their own asymmetry through a plane of symmetry. These compounds are called meso compounds, meso meaning middle. They have chiral centers, but are wholly achiral. But remove the mirror and multiplicity blossoms. When molecules have multiple chiral centers without a mirror internal plane, each center defines an axis of uniqueness. Now there are distinct mirror image pairs, true enantiomers, that cannot superimpose. And between enantiomers lie diastereomers. The same formula, same connectivity, but they are not mirror images. Change one chiral center but not the other, and you create a cousin. Similar yet distinct in properties. The word comes from dia, through, difference flowing through the three-dimensional space. It is important to note that chemical reactions can create or invert chirality. A simple example is provided based upon attacking an sp2 hybridized center from one side or the other. Later we'll see that in substitution, a backside attack will flip configuration, meaning that R will become S and left become right. Enantiomer pairs are not different physically or chemically except in one property: how they interact with plane polarized light. Plane polarized light are waves of light that oscillate in one plane, and they rotate when passed through a chiral medium. One enantiomer will turn it towards the right, which we call dextrorotary, and the other will turn it to the left, which we call levorotary. However, it is important to note that how we label the chirality does not mean that it will be dependent at all on how they interact with light. We end on an addendum to warn against confusing enantiomeric optical activity with the absolute naming convention, R and S, for treating chiral substances, as well as some historical artifacts of convention. We take an example of glucose. Fisher projections at the top orient carbon chains vertically, defining right and left for each chiral center. As we see at the bottom, Haworth projections can curve these chains into rings, showing how intramolecular bonds close to form sugars. The D and L designation for glucose, which is inherited from Fisher, does not refer to dextrorotary and levorotary. Rather, dextrorotary and levorotary is symbolized by positive in parentheses and negative in parentheses, and only refers to optical activity. This is a very common source of confusion, but it needs to be distinguished. And really, the only time you would encounter this is with respect to sugars and amino acids. So we end with our consideration of biological molecules. The world could have formed with these biological molecules, both hands equally. Yet life clearly chose one: right-handed sugars and left-handed amino acids. Thus, every cell, every turn of DNA, every enzyme carries out primordial asymmetry. Till next time, Crip.